In this lecture, we work out an exercise involving similar triangles by using the definitions and properties of the modulus and the argument of a complex number. Let z sub 1, z sub 2, z sub 3, and z sub 4, z sub 5, z sub 6 be two sets of corresponding vertices of two triangles. We consider the determinant where the first column is made up of the vertices of the first triangle, the second column is made up of the vertices of the second triangle, and the third column is all ones. We will prove that the two triangles are similar if and only if the determinant is equal to 0. However, there is one little caveat that we should point out regarding the conditions in the if and only if statement. The if and only if statement is true provided that the two triangles have the same orientation. Now, what do we exactly mean by the orientation of a triangle? Viewed from above, starting with the vertex z1 on the first triangle and following the clockwise direction along the triangle, we get to z2, and then to z3, and then close the triangle at z1. This is often referred to as the negative orientation. Starting with z4 on the second triangle and following the same clockwise direction and therefore the same orientation along the second triangle, we get to z5, and then to z6, and then back to z4. It just so happens that following the same clockwise direction or orientation along the two triangles, the correspondence between the vertices of the two triangles is preserved, and this is crucial to our proof. Should the second triangle have the reverse of the orientation of the first triangle, as in the case now in the diagram, then we take the conjugates of z4, z5, and z6 to obtain what we might call the conjugate triangle of the second triangle. Complex conjugation is the reflection across the real axis. Being a reflection across a line, complex conjugation reverses the orientation of a curve so that now the conjugate triangle has the same orientation as the first triangle. We can then show that the determinant equation is still true, except that this time the second column of the determinant is made up of the conjugates z4 bar, z5 bar, and z6 bar. The proof for this is very similar to what we will show for when the two triangles have the same orientation. We leave this as an exercise for the viewer. So, without loss of generality, we assume that the two triangles have the same orientation. Because the statement is an if and only if statement, there are two statements to consider. One statement or direction supposes that the two triangles are similar. Then we have to show that the determinant is 0. The other direction supposes that the determinant is 0. Then we have to show that the two triangles are similar. Let us first suppose that the two triangles are similar. The two triangles are similar if and only if the corresponding sides are proportional. That is, there should exist a positive real number k such that the distance between z2 and z1, or the absolute value of z2 minus z1, equals k times the distance between z5 and z4, or the absolute value of z5 minus z4, the distance between z3 and z1, or the absolute value of z3 minus z1, equals k times the distance between z6 and z4, or the absolute value of z6 minus z4, and the distance between z3 and z2, or the absolute value of z3 minus z2, equals k times the distance between z6 and z5, or the absolute value of z6 minus z5. We define the transformation t sub 1 of z to be equal to z minus z sub 1 for all complex numbers z. T sub 1 of z1 is 0, so that z1 is translated to the origin. T sub 1 of z2 is z2 minus z1, which we call z2 star. T sub 1 of z3 is z3 minus z1, which we call z3 star. z3 minus z2 equals z3 minus z1 minus the quantity z2 minus z1. z3 minus z1 is z3 star, and z2 minus z1 is z2 star, so that z3 minus z2 is z3 star minus z2 star. T sub 1 is what is called a translation transformation because we are subtracting a fixed point from each complex z. Translations like complex conjugation and reflections across lines preserve distances and angles. So the transformation T sub 1 translates triangle Z1, Z2, Z3 onto the congruent triangle Z1 star, Z2 star, Z3 star. We're giving the origin the alias Z1 star. We define another transformation T sub 4 of Z, which this time is Z minus Z4. T sub 4 of Z4 is also the origin, so the origin has another alias, Z4 star. T sub 4 of Z5 is Z5 minus Z4, which we call Z5 star. T sub 4 of Z6 is Z6 minus Z4, which we call Z6 star. And just as Z3 minus Z2 is equal to Z3 star minus Z2 star, Z6 minus Z5 is equal to Z6 star minus Z5 star. So T sub 4 translates triangle Z4, Z5, Z6 onto triangle Z4 star, Z5 star, Z6 star. And so the proportionality equations are equivalent to these equations. Let an argument of Z2 star be alpha, and let an argument of Z3 star be beta. Let the smallest non-negative angle between the vectors Z2 star and Z3 star be theta. Without loss of generality, we choose alpha and beta so that theta equals alpha minus beta. Z2 star over Z3 star equals the absolute value of Z2 star times e raised to the power I alpha divided by the absolute value of Z3 star times e raised to the power I beta. So Z2 star divided by Z3 star is equal to the absolute value of Z2 star divided by the absolute value of Z3 star times e raised to the power I times alpha minus beta. If it were to happen that we have the opposite situation where alpha minus beta is minus theta, then we would use the reciprocal Z3 star over Z2 star instead of the fraction Z2 star over Z3 star. Assuming now that alpha minus beta is theta, Z2 star over Z3 star equals the absolute value of Z2 star over the absolute value of Z3 star times e raised to the power I theta. For the second triangle, let the argument of Z5 star be delta, and let the argument of Z6 star be gamma. Since between similar triangles corresponding angles are congruent, the smallest non-negative angle between the vectors Z5 star and Z6 star is also theta. And since we have the same orientation for the two triangles, we can choose delta and gamma such that delta minus gamma equals theta. From these equations, we get the absolute value of Z2 star over the absolute value of Z3 star equals the absolute value of Z5 star over the absolute value of Z6 star. And with e raised to the power I theta, we have this equation. Theta is delta minus gamma. The absolute value of Z5 star times e to the power I delta is Z5 star. And the absolute value of Z6 star times e to the power I gamma is Z6 star. Therefore, Z2 star over Z3 star equals Z5 star over Z6 star. Z2 star is Z2 minus Z1. Z3 star is Z3 minus Z1. Z5 star is Z5 minus Z4. And Z6 star is Z6 minus Z4. And we end up with this equation. We cross multiply and multiply things out, move everything to the left side, and then simplify. The viewer can check that the left side is the determinant. And so we have completed the proof of the first direction of the if and only if statement. We will now show that the two triangles are similar if the vertices of the triangle satisfy the determinant equation. We have already seen that the determinant is equal to this quantity, We are assuming it is equal to 0. One can show as an exercise that this equation is equivalent to these equations. We take the absolute value of every numerator and every denominator in the first equation. This fraction is the ratio between these corresponding sides of the two triangles. It is equal to this fraction, which is the ratio between this other pair of corresponding sides. The viewer can check that we also get these equations from the determinant equation. And with the absolute values, this fraction is the ratio between this pair of corresponding sides of the two triangles. Therefore, all corresponding three pairs of sides of the two triangles are proportional, so that the two triangles are similar. This completes the proof of the second half of the if and only if statement and the exercise.